assignments for AP Calculus on the topic of the divergence or nth term test, the integral test, and the p-series test. So there's a lot of different tests to determine if these infinite series converge or diverge. Again, converging means it eventually approaches a specific value. Diverges means it doesn't, usually going off to infinity, or also just could also be bouncing back and forth between two values and never settling on a specific value. So the most basic test on these series, again, you can see they're infinite because they go on forever. This means you would substitute in the first number here for n1, a lot of times it's a common number, but not always, and into the formula a sub n right here. You get the first term, then substitute in 2, then 3, then 4, integers all the way up forever. And then find the sum of those. That's what this sigma means, we're adding them all up. And what the divergence or nth term test says, and you can, there's just two different names for it, you could hear it worded either way, is if the limit as n approaches infinity of this function a sub n, which we use to represent the formula that allows you to find each term, if that does not equal 0, it diverges. Notice that doesn't mean it guarantees it converges if it does equal 0. It just means it might converge. It has the potential to. Versus if it's not 0, it definitely diverges. So that's the only thing it can guarantee you. So to determine whether the series diverges or might converge, and specify what test or tests you're using. So the way the divergence or nth term test works, here again, this is our formula for the nth term, which we call a sub n. And we just find the limit of that as n approaches infinity. So going back to our limits at infinity, whenever you look at on a fraction like this, the terms with the highest exponents matter. So this is going to be just infinity on the numerator over the square root of infinity, infinity to the 1/2. So, and that's infinity over infinity to the 1/2. Simplifies to be infinity to the 1/2. You subtract the exponents, which is just infinity. So notice that's not 0. So this one you can say, if this does not equal 0, infinite, this series diverges by, you can either call it the divergence test or the nth term test. All right, let's take a look at one more using the divergence or nth term test. So in this one again, here's our formula for the nth term. Again, if you substitute 1, that's going to give you the first term, 2 for n gives you the second term, and this sigma means we're adding to summing those all up, and it's an infinite number of terms here. So this time we find the limit again as n approaches infinity. Again, remember in a fraction like this, use the term with the highest exponents. Or it's going to be what matter when you substitute in infinity. So on the numerator, that's the 6 infinity squared, and the denominator, that's negative infinity cubed. So here, 2 of the infinities cancel out. So you end up with 6 over this huge negative number, and whenever there's a infinity left over on the denominator, whether it's positive or negative, 6 over some huge negative numbers is going to be really close to 0. So this one actually does equal 0. So if it equals 0, that doesn't guarantee it converges. It just means the divergence tests show us it might converge. Okay? So that's all we can conclude based on just this test. So we can say it might converge In order to figure out if it does or not, we'd have to use another test. So I'll put another other tests needed. I want to learn about 2 of those other tests today. All right, so that's kind of just basic ones. It can just quickly find some that definitely diverge if that limit's not 0. Most of the ones they give you, though, on the AP test will equal 0, so that you have to use one of the other tests. But if you see one that doesn't equal 0, you can tell right away it diverges by the nth term or divergence test. All right, so the next test we're going to look at is the integral test. So this says we've got an integral, and notice n equals 1 here. That becomes the lower limit. And then infinity becomes the upper limit. A sub n, again, is our formula here. And f of n, if they're equal to each other, these two are the exact same formula, either both converge or both diverge. Okay? And this works if f is positive, continuous, and monotonically decreasing, which usually the functions they give you are, for n is greater than or equal to 1. So, let's take a look here and see. We're basically going to see if the integral converges or not, and then base whether our series will converge or not based on that. So the way you can tell is if the formula here is something that we are able to integrate. In this case, you can see if you plugged in infinity, you would get 0. We have infinity's left on the number, so the divergence test would only tell us it might converge. So, using the integral test, we can rewrite this series as a similar integral here. It would be the integral from 1 to infinity of n over n squared plus 1, and then dn. Just a little different than the variable n instead of x or t. Same process here. So, in order to integrate this one, you can see you'd have to use u substitution. And this is one where if you set u equal to the denominator, n squared plus 1, and then find the derivative, du dn would equal 2n, and then solve it for dn. So dn would equal du over 2n, and we'll be able to substitute that in for dn right there. And remember, on these definite integrals, you also have to convert these. So you substitute in infinity. And it'll be infinity squared plus 1. So the plus 1 is negligible, so we just have infinity squared. We substitute 1, we get 1 plus 1 is 2. And then we still have this n over, now we replace that whole denominator with u. And then the n we figured out is u over 2n. And then we can see the n's reduce out, which is what we wanted. Get all in terms of u. We can pull out the 1/2 out the front. And then we're just left with the integral from 2 to infinity squared of 1 over u. And then we can integrate that. So I've got 1/2. When you integrate 1 over u, sorry about the bell there, we get natural log absolute value of u, evaluated from 2 to infinity squared. So 1/2. In this case, both of them were positive, so the absolute value is not going to have an effect. Natural log of infinity squared minus natural log of 2. You can see this natural log of infinity squared, that's not going to cancel out with anything. That's just going to be infinite. And so since we get infinity here, that means this diverges. And since the integral diverges, the integral test says either both converge or both diverge. That means the series is also going to diverge. So you can say this one diverges by the integral test. All right, let's take a look at another example here. integral test. So again, the way you can tell you can use the integral test, and sometimes there's more than one test you can use. It's not like every problem there's only one test that works. Sometimes there is, but sometimes you can get the same answer with different tests. That can happen. So on this next one here, again, this is something we can integrate. So if we just rewrite this, it's an integral from 1 to infinity, n cubed e to the negative n to the fourth, and dx. So again, we're making this a sub n the thing we integrate here. Remember, a sub n is the same as f of n, the function we integrate here. So here again, there's another one that requires u substitution. You can see on this one, the function inside is our exponent, negative n to the fourth. So when you find the derivative of that, du dn, we get negative 4n cubed. And then solve it for dn. So dn equals du over negative 4n cubed. And we can substitute that right in here. And again, we can also convert our upper and lower limits here. So when you substitute infinity and then 1 in there, substitute infinity, notice the negative's out in front, so it actually becomes negative infinity to the fourth. And we substitute 1 to the fourth is 1, there's a negative, so negative 1. And then we still have the n cubed, and then it's e to the u. And we replace the dn with du over negative 4n cubed. And then again, you can see the n cubes reduce out, which is what we want. Get it all in terms of u. You can pull out a negative 1/4 on the outside. Also, what you can do is notice these are actually in the wrong order now, so you don't have to do this, but you can flip them and then just make it change the sign so it's a positive 1/4. And then the negative infinity to the fourth, the lower limit will go here, upper limit negative 1 there. And then we just have e to the u d, something we can integrate. So remember, when you integrate e to the u, that's the one that stays the same. You just get e to the u. You got a 1/4 on the outside. And that's evaluated from negative infinity to the fourth to negative 1. Then go 1/4 e to the negative 1 minus e to the negative infinity to the fourth. So if we simplify that, that's 1/4. We get rid of the negative exponents, it'll be easier to analyze. This is 1 over e minus 1 over e to the infinity to the fourth power. Well, 1 over e, that's just close to 1/3 here. That's about 1 over 2.7. But 1 over e to the infinity to the fourth, that's a huge number on the denominator. That's going to be 0. So all we're left with is 1/4 times 1 over e, so 1 over 40. So notice, unlike the previous problem, we got a specific answer here, which means it converges. We didn't get infinity. We didn't get something that diverges. So, and remember, with the integral test, either both converge or both diverge. So the integral converged, so that means the series would also converge by the integral test. So we can say this one converges by the integral test. All right, let's take a look at one more test. Okay, and this is probably one of the easier tests to apply quickly, and that's called the p-series test. And the p in this case refers to the exponent of n that's on the denominator. So what this is saying, if you rewrite it this way with the n on the denominator, which these will usually be, or you can rewrite it this way, since if the n was on the numerator, it wouldn't approach 0. You could use the nth term or divergence test to show it diverges. But if it's on the denominator, it could converge sometimes or diverge, and it really depends if it's in this form based on the exponent. So if that exponent is greater than 1, even if it's like 1.1 or something, then it converges, but if it's less than or equal to 1, really you won't have a case where it's 0, because then it would just be 1, or where it's negative, because then it would just end up on the numerator. So we'll use it for these to fit the p-series. If it's less than or equal to 1, then it diverges. So on this first one here, you can see there's a 1 right there, so p is equal to 1. And notice the equal to is right here. So this one diverges by the p-series test. Then the next one here, if we rewrite this, you can see this is 1 over n to the 3 halves. So p is equal to 3 halves here. And notice that's greater than 1. It's 1.5, so this one converges by the p-series test. All right, the next one you can see is written with a negative exponent. We can easily rewrite that as 1 over n cubed. So if you rewrite it that way, then you can see p is equal to 3, which again is greater than 1. So this one also converges by the p-series test. And then this one, sometimes you might have it written as a decimal. P in this case is equal to 0.8, but notice that's less than or equal to 1. So this one diverges by the p-series test. So again, once you have it in this form here, you can tell what the exponent p is equal to and determine whether that diverges or converges based on the value of p. Okay, so one other thing to note here, this first one that we went over, right where the equal to is, right there, 1. When you have this series from 1 to infinity of 1 over n, that has a special name you sometimes might hear. It's referred to as the harmonic series. And the pattern on that, notice what would happen if you plugged in 1, then 2, then 3. The first one you get 1, then you plug in 2, it'd be 1 plus 1/2, plus, then you plug in 3, 1/3, plus 1/4, and that goes on forever. And now when actually, as we saw here by the p-series test, the harmonic series actually diverges. All right, let's take a look at the next problem here. So this one asks for the first 3 partial sums of the series. Okay. So the partial sums, the first sum is the same as basically the first term. A sub 1 when you plug in 1. The second sum, second partial series, is the sum of the first 2 terms, a sub 1 plus a sub 2. And the third partial sum is the sum of the first 3 terms, first term plus the second term plus the third term, and so on. So each time you get the next partial sum, it's getting you closer and closer to the infinite series, which goes on forever, has all the terms. So that's what it means by the partial sum series. So let's find that part first and then figure out if the series converges or diverges. All right, so for the first partial sum, you always again start with this number, which oftentimes is 1 but not always. Substitute that in for the ends to get the first term. So a sub 1 would equal 1 e to the negative 1, which is just 1 over e. So that's what the first term is, and that's what the first partial sum is, just 1 over e. Then, to get the second term, you would substitute in 2. So that would be 2e to the negative 2. So this would be 2 over e squared would be the second term. And the second partial sum, you take these two terms added up. So it would be the first term 1 over e plus the second term 2 over e squared. That would be our second partial sum. And then to get the third term, you would substitute in 3. So it would be 3e to the negative 3. So it would be 3 over e cubed. So the third partial sum would be the sum of the first three terms. So the first term was 1 over e, plus the second term was 2 over e squared, plus the third term is 3 over e cubed. And you can keep going like that if you needed the fourth partial sum and so on. But it allows you, with having three terms there, you can start to see the pattern, oftentimes, of the terms here. And then, of course, the series here means this going on forever. The series is the sum of all the terms. That's why these are called partial sums. When you do a part of a sum that eventually does go to infinity. Because you do a picture of what it's going to look like. So, to see if it converges or diverges, well, you could first try the nth term test. Really quickly here. Find the limit as n approaches infinity of our formula here, a sub n. That would be infinity e to the negative infinity. So you have infinity over e to infinity, but e to infinity, remember, is exponential, is larger than the polynomial here. So this one actually is going to equal 0. So if it wasn't 0, we'd know it diverges, but since it is 0, that means it might converge. And you can see this one doesn't fit the p-series, so far the only other test we have is the integral test. Or we have the integral here from 1 to infinity of our a sub n e to the negative n dx. And you can see in this one, u substitution wouldn't work here because the derivative here of, if we said u equal to negative n would just be negative 1. That's not going to cancel off this n, but we have things multiplied together. So this one's going to require integration by parts. So remember, we want to set the one that simplifies better, usually equal to f of x, or in this case f of n. So n would simplify more, so and let's set the other one equal to g prime of n. And then we find the derivative of this one is 1. And integrate this one using the u substitution shortcut. The derivative of negative n would just be negative 1, so you divide by that. The e part stays the same. And notice this one, if you want to save a little time, we can use the tabular method here, since the derivative of this eventually is going to be 0. So the next one, double prime be 0. When this one eventually becomes 0, you can use the tabular method on those, although you don't have to. And then this one, we integrate again. We don't really have a notation for it, so I'll just put down what it is, the antiderivative here. Again, using substitution here. Shortcut, you divide by another negative one, which is going to cancel out that. So remember with integration by parts, the way it works is you group them like this, f times g, because that's the first part of integration by parts. So the first part's going to be n times e to the negative n over negative 1. And then the next one, I'm going to group these two together, but this is going to be a minus, because it alternates, because the minus in the formula there. So it's going to be minus 1 times e to the negative n. And this is evaluated from 1 to infinity. This is the definition here. So we can simplify this a bit. Notice to make it a little simpler, they both have a negative, so you could, although you don't have to, factor out the negative out in front, so you don't have to worry about it. And then this first term would just end up being n. We get rid of the negative exponent, easier to simplify, over e to the n. And then now it's going to be plus, since we factored out the negative. This one would just be 1 over e to the n. So we have a negative on the outside. And then if we plug in infinity, first we have infinity over e to the infinity plus 1 over e to the infinity minus 1 over e plus 1 over e. That's what gets plugged in 1. So infinity over e to the infinity, again, e to the infinity is much larger, so this one's going to be 0. And 1 over e to the infinity, that's also 0, so those are wiped out. Then if you distribute the negative, times this one, it cancels out this negative. So all that's left is 1 over e plus 1 over e gives you 2 over e. So notice we got a specific number. It's not infinite, so that means it converges. And we use the integral test. So this converges by the integral test. Let's take a look at this one here. First three partial sums again. So A1, we just started with this number here, so it would be 2 over the square root of 1, would just be 2. So our first partial sum, S of 1 is the same as the first term, just 2. Then the second term, you'd substitute 2, so you get 2 over root 2. Which you could simplify if you want, but you don't have to if you want to multiply by root 2 over root 2. That'll give you 2 root 2 over 2, so that's just going to be root 2. Because the 2 here and the 2 here can't reduce out. So our second partial sum, the first term plus the second term, so that would be the first term is 2, plus the second term is root 2. And then the third partial sum, plug in 3, 2 over root 3. Again, you could leave it like this or simplify it. Multiply by root 3 over root 3 would give you 2 root 3 over 3. So the third partial sum would be the sum of the first three terms, 2 plus root 2 plus 2 root 3 over 3. So those would be our first three partial sums. Then this one, notice, you could use the integral test. This is not that hard to integrate, but in this case, notice it fits the p-series except for this 2 here. But just like we do with integrals, with series, you can pull constants out in front. So we can pull that 2 out in front. And it really just multiplies the whole answer by 2. And then, notice what we're left with, 1 over n to the 1/2. That does fit the p-series. P is equal to 1/2. And that's less than or equal to 1. So that means this diverges by the p-series test. And that concludes the notes for AP Calculus on the topics of the divergence test, also called the Nth Term Test, the integral test, and the p-series test.